So in this lecture, I will speak about the geometric Hahn-Banach theorem. So I will start with the definition, and let me just remind that throughout this lecture, X will be a linear space over the reals. So the field will be the real numbers, since we proved the Hahn-Banach theorem in this context. So let me go back to my definition. If I have a set S, which is a subset of X, and I have a point X in S, X will be said to be an interior point of S if for all y in X there exists an epsilon, which depends of course on y, such that X plus ty belongs to S for all t whose absolute value is bounded by epsilon. So X will be said to be an interior point if for any y you can find an epsilon such that X plus ty belongs to S for all t smaller than epsilon in absolute value. So this means that you have a set here S, you have here a point X, and let's say that you have the origin. I'm thinking here of a vectorial space. So here is y. So this means that here is x plus y. Let's say that x plus y. And what this condition is requiring is that in this direction, you take x plus epsilon or ty, which is all these points here, all this interval of points, it's contained in the set S. Of course, this epsilon depends on y, so it's not true that the fact that X is an interior point does not imply that you can find an epsilon such that the ball of radius epsilon centered at X is contained in S. This is not true, because, well, the epsilon is depending on y. So if you take on one direction, you have one epsilon. You could take another direction, a smaller epsilon, another direction, a smaller, and go smaller and smaller. And in this sense, you won't be able to find an epsilon which works for all directions. Of course, in infinite dimension. Of course, in finite dimension, this will be true. So this is the definition of interior point. So let me now define an object. So I'm assuming that I have K, which is a convex set. So a convex subset of X. And I have a point X in K, which is an interior point. And now I'm defining a function p from x to r plus, which will depend on the convex set and on x. So actually p is a function of p, k, and x, and it's defined as follows. You take a point y in x, and p of y will be the infimum of all a positive, such that x plus 1 over a y belongs to k. Right? Well, this is well defined. Let me just first observe that p of y is finite, because since x is an interior point, you know that there exists an epsilon such that x plus t y belongs to k if t is smaller than epsilon. This is by definition of interior points. So this means from that you conclude that, well, x plus epsilon times y belongs to k. And I can rewrite that, of course, as 1 divided by 1 over epsilon y. And this means that 1 over epsilon belongs to this set of a's such that x plus 1 over a y belongs to k. So this point 1 over epsilon belongs to this set, and therefore the infimum, which is p of y, it's smaller than 1 over epsilon. So p of y is smaller than 1 over epsilon, and therefore it's finite. So this shows that since x is an interior point, p of y is well defined and it's finite. Then I just copied here the definition of p. P is called the gauge function. And well, you see from the definition that p will be positive. We will show in a moment that p is positive homogeneous and subadditive. But before proving that, let me just observe the following. Assume that b belongs to the set of a's such that x plus 1 over a y belongs to k. This means that, well, x plus 1 over b y belongs to k. What I claim is that if I take a b prime which is larger than b, then b prime also belongs to the set A such that x plus 1 over a y belongs to k. Okay. So what I'm claiming is that as soon as, if you have a point b which belongs to this set, then any point b prime, any real number b prime larger than b also belongs to that set. And this follows from the fact that k is convex. So you know that x plus 1 over by belongs to k. You also know that x belongs to k by assumption. And therefore, any convex combination of these 2 points belongs to k because k is convex. So this means that for all theta in 0, 1, theta x plus, maybe let me write it as 1 minus theta x, it will be easier this way, plus theta times x plus 1 over b y belongs to k, right? Because I'm taking a convex combination of 2 points which belong to k, yes. Now, I have here 1 minus theta x plus theta x, this is x, plus theta by belongs to k, and this for all theta between 0 and 1. So I can rewrite this as x plus 1 over b divided by theta y belongs to k, and what remains to be done is to choose theta such that b over theta it's equal to b prime, which means that let me take theta to be b divided by b prime, which indeed belongs to 0, 1, right? Because b prime it's larger than b, and all these infimums are over a positive, so b it's strictly positive, and therefore theta, which is b divided by b prime, belongs to 0, 1. So if you choose that theta, you know that x plus theta divided by b y belongs to k, which means that with this choice we get that, and therefore b prime belongs to that set. So this means that this set will be either, since we know that once B belongs to that set B prime, larger than B belongs to that set, this means that this set, it's an interval either of A0 plus infinity or A0 plus infinity. So the set of A's positives for which x plus 1 over A y belongs to K, it's a semi-infinite interval which might be either open on the left or closed on the left, but in any case it will always be a semi-infinite interval. So here comes the proposition I announced. I claim that the function p, which is defined over x to r plus, is positive homogeneous and subadditive. So let me start by proving that it's subadditive. So what I want to show is that P of, say, Z1 or Z plus Y is less or equal than PZ plus PY. We have seen that PZ and PY are finite. So there exists for, let's say, Z, there exists here. So I haven't written that A is positive, but remember that here I'm taking the infimum of all positive A's for which this happens. So since PZ is given by this infimum, and this infimum is finite, I can always find an A which almost attains the infimum. So there exists, let's say, an A which is positive such that, well, P of Z, which is the infimum, is less or equal than A, which is less or equal than PZ plus epsilon. Right? So I can find an A which almost, well, let me call it maybe A0. So there is an A0 which almost attains this infimum for Z, which means that well, PZ, which is the infimum, will be smaller than this A0, but this A0 will be smaller than PZ plus epsilon if I fixed an epsilon positive. So I started by fixing epsilon, and then I can find this A0. In the same way, I can find a B0 for Y. So there exists a B0 which is strictly positive, such that, well, P of Y, it's smaller than B0, which is smaller than P of Y plus epsilon. Now I claim that x plus, well, I know that x, this A0 belongs to this set, so I know that x plus 1 of A0 Z belongs to K, and x plus 1 over B0 Y belongs to K. Right? I'm considering the infimum of A, so I found one element in this set which almost attains the infimum, so A0 belongs to that set, which means that x plus 1 over A0 Z belongs to K, and in the same way, x plus 1 B0 Y belongs to K. Now, I will use convexity by saying that any convex combination of these two elements also belongs to K because K is convex. So I know that for all theta in 0, 1, theta times x plus 1 over A0 Z plus 1 minus theta x plus 1 over B0 Y, this belongs to K. And so now I can choose freely theta in 0, 1. So let's sum. On the one hand, we have theta times x plus 1 minus theta times x. This gives me x. And then plus theta a0 z plus 1 minus theta divided by b0 y. And okay, I need some space, so let me erase these conditions on this definition. And what I would like is to get here the same coefficients as here, so that I have z plus y appearing. So I want to choose theta in such a way that theta divided by a0, it's equal to 1 minus theta divided by b0. Because if I have that, the coefficient multiplying z will be the same as the one multiplying y, and therefore I will have z plus y, and this will give me an indication about p of z plus y. So, well, from this equation, I get that theta times b0 plus a0 is to be equal to a0, and which means that theta, the theta I want to choose, it's a0 divided by b0 plus a0, and therefore 1 minus theta will be equal to b0 divided by a0 plus b0. So with this choice, I get that theta divided by a0, theta divided by a0, it's 1 over. So this element here belongs to k, right? Because it's this one which belongs to k. So now I'll set theta as a0 divided by b0 plus a0, which is indeed an element in the interval 0, 1. And I'll just replace theta by this value. And what I get is that x plus theta divided by a0, it's 1 divided by b0 plus a0, and this is multiplying z, plus 1 minus theta divided by b0, it's again 1 over a0 plus b0, and this is multiplying y, that this element belongs to k. This means that x plus 1 over b0 plus a0 times y plus z belongs to k. And this means that b0 plus a0 belongs to this set if instead of y I have y plus z, right? I just have shown that x plus this factor, this scalar multiplying y plus z belongs to k. This means that b0 plus a0 belongs to this set if I have here y plus z instead of y. And therefore, p, this implies that p of y plus z, it's less or equal than a0 plus b0. Because p of y plus z is the infimum, and we know that this number, this real number, b0 plus a0, belongs to that set, so it is larger than the infimum. But on the other hand, I have that, well, we chose a0 and b0 in such a way that these two inequalities are in force, and this means that this is less or equal than py plus pz plus 2 epsilon. And this inequality holds for any epsilon, because we started by choosing epsilon. We can set epsilon to 0 to get that pi y plus z, it's bounded by pi y plus pz, which is the inequality we wanted to prove. Let me now show that p, it's positive homogeneous. So let's fix alpha positive, and what we want to prove is that p alpha y, it's equal to alpha p of y. Well, what is P of y to P of y, alpha y? It's the infimum of all a positive such that x plus 1 over a y belongs to k. So let me consider the set. So this is the set of all a positive such that x plus, I'm sorry, there is a alpha here, right, because I'm taking alpha y. So the set of all a such that x plus alpha a y, so it belongs to k. So this is the set. And here, well, I can write a as alpha a. So this is the set of all, if I replace a divided by alpha by b, so this is the set, this corresponds to the set of all alpha b positive such that x plus by belongs to k. And this is, of course, the set, the alpha times the set of all b's such that x1 over b. But I'm taking b to be a divided by alpha, so this is 1 over a divided by alpha, therefore 1 over b, sorry. So this is the set of all alpha b's positive such that x plus 1 over b y belongs to k. Since alpha it's positive, this is exactly equal to the set of alpha times all b's such that x plus 1 over b y belongs to k. Therefore, if I take, well, the infimum of this set, and this set corresponds to this set, it's equal to alpha times the infimum of this set. So P of alpha y, it's equal to the infimum of this set. This set corresponds to this set. So this is also equal to the infimum of alpha of all b is positive such that x plus 1 over b y belongs to k. And this alpha can get out of this infimum, and what remains is p of y. So from this identity, we get that indeed, if alpha is strictly positive, p alpha y is equal to alpha p y for any y, and that proves that p is a positive homogeneous function. So now I claim the following new proposition, so that if x plus y belongs to the convex set K, this implies that P of y is less or equal than 1. And so that's a claim. And the second claim is that x plus y is an interior point of K if and only if P of y is smaller than 1. So let me prove this proposition. So let's first assume that x plus y belongs to K. Well, but if x plus y belongs to K, this means that if you look at this definition of P, this means that A equal to 1 belongs to this set. So 1 belongs to the set of A positive such that x plus 1 over AY belongs to K. And since 1 belongs to this set, this implies that P of y, which is the infimum of this set, it's less or equal than 1. And this proves the first claim, which is very simple. So now let me prove the second one, and I will start by assuming that x plus y is an interior point of K, and then I will show that P of y is strictly smaller than 1. So let me assume that x plus y is an interior point of K. Well, but if x plus y is an interior point, if you remember, this means that for all z in X, there exists an epsilon which depends on z, such that x plus y plus tz belongs to K for all t such that the absolute value of t is bounded by epsilon. Well, I will use this property for z equal to y. So I know that there exists, say, a delta such that x plus y plus t of y belongs to K for all t such that t, the absolute value of t, it's less or equal than delta. Fine, so let me take t equal to delta. So this tells me that x plus 1 plus delta y belongs to K. And I can rewrite this property as x plus 1 divided by 1 plus delta y belongs to K. Right, so now if I look at this definition, this means that this point, 1 over 1 plus delta belongs to the set of a's positive such that x plus 1 over a y is in K. And since this point belongs to this set, the infimum is bounded by 1 plus delta. This means that P of y it's less or equal than 1 divided by 1 plus delta, and this is strictly smaller than 1. So this proves that indeed, if x plus y is an interior point of K, then P of y is strictly less than 1, which is one of the claims. So to complete the proof of the proposition, I need to show that if P of y is smaller than 1, then x plus y is an interior point of K. So to show that x plus y is an interior point, what I need to show is that if you fix z in X, I have to prove that there exists an epsilon such that x plus y plus tz belongs to K for all t less or equal than epsilon. This is what I need to prove. So let's fix z. And now let's see our assumption. Our assumption says that P of y is strictly smaller than 1. So this infimum is strictly smaller than 1. So this means that I know that there exists a strictly smaller than 1 such that x plus 1 over a y belongs to K. And so if I take b to be 1 over a, I get that b is strictly larger than 1 and that x plus by belongs to K. So this is first consequences of our assumption is that I can find a b strictly larger than 1 for which x plus by belongs to K. And now I will use the fact that x is an interior point. So from the fact that x is an interior point, for that z, I know that there exists a delta such that x plus tz belongs to k for all t smaller than delta. So I have two informations. I know that x plus by belongs to k, and x plus tz belongs to k if the absolute value of t is smaller than delta. Now I will use convexity to take a convex combination of these two and to get that x plus y plus tz belongs to k if t is sufficiently small. So let me take, so I know that this element belongs to k, this element belongs to k. Then I know that for all theta in 0, 1, the convex combination of these two also belongs to k. So theta times x plus tz, maybe let me place it here, 1 minus theta, plus theta x plus by, that this belongs to k. And this belongs to k for all theta smaller than delta, right? Well, so now if I compute this sum, what I get is 1 minus theta x plus theta x, so this is x. Then I have plus 1 minus theta tz and plus theta by. So this belongs to k. Now I'll choose theta and, well, look at what we want to prove. Look at this expression. So it's clear that we'll choose theta as 1 over b. b, it's larger than 1. So 1 over theta will be, so theta will be, which is 1 over b, will be smaller than 1. So let me choose theta to be 1 over b, which is indeed an element of 0, 1, because b it's larger than 1. So with that choice, 1 minus theta is 1 minus 1 over b. So this is b minus 1 divided by b. So what we have is that x plus b minus 1 b tz plus y belongs to k. So we just proved that for all t smaller than delta, this element belongs to k. But now if I set s to be b minus 1 b t, what I get is that s, which is b minus 1 b modulus t, and this is smaller than b minus 1 b times delta. So if I set that to be epsilon, I have that x plus y plus s times z belongs to k. This is what I claim. I claim that for all s whose absolute value is bounded by epsilon, where epsilon is given by this expression, this belongs to b. And why is that so? Well, because if s is bounded by epsilon, this means that theta is bounded by delta, and on the other hand, we know that this element belongs to k. So this proves that provided s is bounded by epsilon, I have that this expression belongs to k. So maybe I'm not very clear, so let me insist on that. What I claim now is that if s is smaller than epsilon, then this happens. Why is that so? Well, assume that s is bounded by epsilon, define t as b divided by b minus 1 times s. Then t, which is, it's indeed bounded by b minus 1 s. The absolute value of s, it's bounded by b minus 1. Sorry, here's b. Let me go back. I'm assuming that s, it's bounded by epsilon. So let me define t in this way. So take the absolute value of t. It's equal to that. So this is bounded, therefore, by b minus 1, the absolute value of s. The absolute value of s, it's bounded by epsilon. But epsilon, it's b minus 1 b times delta. So indeed, I have that t, it's bounded by delta. And I proved that x plus this expression, but b minus 1b t z plus y belongs to k, provided that t is less than epsilon. T less than d delta. And indeed, t, it's less than delta. So I know that this expression belongs to k, but b minus 1 b t, it's exactly s. So this proves that x plus s z plus y belongs to k, and this is what I claimed. So this proves that indeed, if py is less than 1, then x plus y is an interior point of the convex set K. Well, the proposition I just proved has a converse, so it's a new proposition. Assume that I have a function p, which is defined on x, take value on r, and which is positive homogeneous and which is subadditive. Then what I claim is that if I define by A the set of all points x in x such that P of x is less or equal than 1, then this is a convex set. And my second claim is that now if I define B to be all points x in x such that P of x it's strictly less than 1, then B is convex and the origin is an interior point. Of B. So let's prove this proposition. Well, let's define A as the points such that P of x is less or equal than A. I want to show that A is convex, so let me take x and y in A, theta in 0, 1. And what I want to prove is that theta x plus 1 minus theta y belongs to A. But to prove that theta x plus 1 minus theta y belongs to A, well, what's the definition of A? These are all points for which P of x is less or equal than 1. So I have to show that P of this quantity is bounded by 1. So P of theta x plus 1 minus theta y by subadditivity, this is bounded by P of theta x plus P of 1 minus theta y. Now theta, it's an element between 0 and 1, so it's non-negative. So by subadditivity, this is, by positive homogeneity, this is equal to theta P of x plus 1 minus theta P of y. And since x and y belongs to 1, P of x is bounded by 1, P of y is bounded by 1. So this is bounded by theta plus 1 minus theta, which is equal to 1. And this proves that indeed the set is convex because theta x plus 1 minus theta y belongs to 1. The same proof applies for the first statement of my second assertion. So now I define B as all points for which P of x is strictly less than 1. And what I claim is that the same proof shows that B is convex. So let's take here x and y in B and theta in 0, 1. So I have to show that theta x plus 1 minus theta y belongs to B. So to prove that theta x plus 1 minus theta y belongs to B, I have to show that P of this element is bounded strictly less than 1. So P of theta x plus 1 minus theta y, by subadditivity, it's bounded by P theta x plus P 1 minus theta y. Now by positive homogeneity, since theta is positive and 1 minus theta also, this is equal to theta px plus 1 minus theta py. But x belongs to B, so that px is bounded by 1, strictly less than 1. The same for y. So theta px plus 1 minus theta py is strictly less than 1, which means that theta x plus 1 minus theta y belongs to B. And therefore, the first claim of the second assertion is proved. What remains to be done is to show that 0 is an interior point of B. So remember, what remains to be done is we have a function P which is positive homogeneous and subadditive. We define B as all points for which P of x is strictly smaller than 1, and we want to show that 0 is an interior point of B. Well, of course, the origin belongs to B because, well, P of 0, it's equal to P0 times 0, and by positive homogeneity, this is P0, 0, and this is equal to 0. So P of 0 is 0, and it's less than 1, so 0, of course, belongs to B. And to show that it's an interior point, what we have to prove is that you fix x in x. You want to show that 0 plus tx belongs to B for all t less than epsilon. So you want to prove that for that fixed x, there exists an epsilon positive such that 0 plus tx, which means tx, belongs to B for all t smaller than epsilon in absolute value. So fix that x. Well, I know that P of x is finite. Right? P of x, it's just a number. So let me take, and the same thing for P of minus x, which is also finite. So now, let me claim that if I take t of x and I compute that, let's say for t positive, I compute P of tx. So this is t times px, and that will be smaller than 1, provided that t is smaller than P of x. And here, I don't know if I made that precise, but I'm assuming that P takes values from x to r plus. So I'm assuming that P take only non-negative values. Now, suppose that t it's negative. Well, P of tx, I can rewrite P of tx as P of minus t times minus x. Minus t now it's positive, so by homogeneity this is times minus t p minus x, and therefore this is less than 1 if, well, remember minus t it's negative, so minus t it's positive if minus t it's smaller than 1 over p minus x. So now if I take epsilon to be the minimum of 1 over px and 1 over p minus x, and these two values are positive numbers and finite, because p is defined on over all space. If I take p, well, let's say maybe divided by 2, what you get is that if t it's smaller than epsilon, then indeed ptx belongs, so what I claim is that this implies that tx belongs to B. So to show that 0 in an interior point, I have to find epsilon. Here is what I propose for epsilon, 1/2 of this minimum. And for that epsilon, I want to show that tx belongs to P if the absolute value of t is less or equal than epsilon. So take a t for which the absolute value is less than epsilon. Well, assume that t is positive, then ptx is equal to tpx, but t it's smaller than epsilon, so in particular it's strictly smaller than 1 over px, and therefore this number is smaller than 1. In the same way, if t is negative, then ptx is equal to minus t times p minus x, and since the absolute value of t is bounded by epsilon, this quantity here is smaller than 1 because epsilon it's strictly smaller than 1 over p minus x. Therefore, we prove that, and this shows that indeed 0 is an interior point of P.